Now let us meet another important building block inside the microcontroller: flash memory. Flash memory is where our program lives. Everything we write in our Arduino IDE or any other embedded firmware development platform is eventually stored here. You can think of flash memory as a permanent library of instructions. Just like books stay on the shelves of a library, our programs stay safely inside flash memory. Even when the power is turned off, the information does not disappear. That is why flash memory is called non-volatile memory. It remembers. When you switch on the microcontroller again, the CPU immediately knows where to find the program and what instructions to execute. The CPU continuously reads instructions from flash memory while the system is running. These instructions might tell the system how to start up, how to read sensors, how to control motors, how to communicate with other devices, or how to handle errors safely.
All of that knowledge is stored permanently inside this memory. Of course, we can update the program whenever we need to. When we upload new code from our computer, we are actually rewriting the contents of flash memory. Modern flash memory can be rewritten many thousands of times, which is more than enough for most engineering applications. So, whenever you press the Upload button in the Arduino IDE, remember what is really happening. You are placing a new book into the microcontroller's permanent library. And every time the system powers on, the CPU opens that book and follows its instructions. Flash memory never forgets. That is why your system always knows exactly what to do, even after the power has been completely turned off.
Now let us meet another very important building block inside the microcontroller: RAM. RAM stands for Random Access Memory. You can think of RAM as the working table of the microcontroller. When we are doing a project, we place the tools, notes, and parts that we need right now on our workbench. RAM works exactly the same way. It stores the information that the program is using at this very moment. For example, sensor readings might be stored in RAM. The current motor speed might be stored in RAM. Counters, target positions, error flags, and calculation results all live in RAM while the program is running. The CPU constantly reads information from RAM, changes values, performs calculations, and writes new results back into it. That is why RAM is designed to be extremely fast. The CPU can read and write to it millions of times every second.
But there is one very important difference between RAM and flash memory. Flash remembers even when the power is turned off. RAM does not. As soon as the power disappears, everything stored in RAM is lost. It is just like a workbench or a notepad. While you are working, everything you need is right there in front of you. But if you clear the table and walk away, all those temporary notes and arrangements disappear. That is why we call RAM temporary memory. It is not meant for permanent storage. It is meant for active work. So remember this simple idea. Flash memory stores what the system must always remember. RAM stores what the system is thinking about and working on right now. RAM is the CPU's fast working space, helping it think, calculate, and control the real world in real time.
Now, let us go even deeper inside the CPU itself. Inside the CPU, there is a very special set of tiny storage locations called registers. Registers are the CPU's fastest tools. If RAM is the CPU's workbench, then registers are the tools that the CPU keeps directly in its hands. Because registers are located inside the CPU, they can be accessed extremely quickly. In many cases, the CPU can read or write a register in just one clock cycle. That is why registers are even faster than RAM. Of course, this speed comes with a trade-off. Registers are very small. There are only a limited number of them, and each one usually has a specific purpose. Some registers store temporary data during calculations. Some point to the next instruction that the CPU must execute. Others keep track of the stack, which is used when calling functions. And some registers store important status information, such as whether the result of a calculation was 0 or whether a carry occurred. There are also general-purpose registers that programmers and compilers use to perform everyday operations.
You can think of registers as the pockets on a craftsman's apron, where he keeps the tools and materials he needs most frequently. The right tool is always immediately available, allowing the work to happen quickly and efficiently. The CPU works in exactly the same way. For every instruction it executes, it constantly uses its registers to hold data, perform calculations, track addresses, and make decisions. This is one of the secrets behind the incredible speed of modern processors. Registers may be tiny, but they are absolutely essential. They are the CPU's fast tools, helping it execute millions of instructions every second and keeping the entire system running smoothly.
So far, we have met the CPU, flash memory, RAM, and registers. Now, let us meet another important group inside the microcontroller, the peripherals. Peripherals are specialized hardware blocks that perform specific jobs for the CPU. You can think of them as skilled workers in a factory. The CPU acts like the manager. It makes decisions and coordinates everything. But the actual work is done by many specialized workers, each with their own expertise. For example, timers keep track of time and create events at precise moments. The ADC, or analog to digital converter, measures real-world signals, such as temperature, light, or voltage, and converts them into digital values that the CPU can understand. Communication modules like UART, SPI, and I2C allow the microcontroller to exchange information with other devices. PWM modules help control motor speed, LED brightness, and many other outputs.
And watchdog timers continuously monitor the system and can restart it if something goes wrong. These peripherals work automatically in the background. This means the CPU does not have to do everything itself. Instead, it can focus on thinking, making decisions, and coordinating the entire system. This makes embedded systems faster, more accurate, and more reliable. Think about some everyday examples. A timer can blink an LED every second without the CPU constantly counting. An ADC can read the temperature from a sensor. A UART peripheral can send data to a computer or receive commands from another device. A PWM module can control the speed of a motor. And a watchdog timer can keep the entire system safe. The important idea is this. Peripherals are the specialized workers inside the microcontroller. They do the work so that the CPU can make better decisions and manage the whole system more efficiently. Together, they make embedded systems smarter, faster, and more reliable.
So far, we have explored what happens inside the microcontroller. But how does this tiny chip connect to the outside world? The answer is through its pins. Pins, or input and output pins, are the connection points between the microcontroller and real devices. You can think of them as the doors and windows of a house. The microcontroller lives inside the house. Through the doors and windows, information comes in and actions go out. Some pins are used as inputs. They allow the microcontroller to receive information from the real world. For example, a push button can tell the system that someone has pressed a switch. A temperature sensor can provide temperature readings. A light sensor can measure the brightness of the environment. Other pins are used as outputs. They allow the microcontroller to control external devices. An output pin can turn on an LED. It can drive a motor to
Or it can send information to a display so that users can see important data. Many pins can also be used for communication. They support interfaces such as UART, I2C, SPI, and even CAN networks. These communication channels allow the microcontroller to exchange information with sensors, memory devices, computers, and other controllers. One important point to remember is that pins are programmable. We can configure them as inputs or outputs depending on the needs of our application. They also operate at specific voltage levels, such as 3.3 volts or 5 volts. Without pins, the microcontroller would be completely isolated from the real world. It could think and process information, but it would never be able to sense anything or control anything. So the big idea is simple. Pins are the bridge between the microcontroller and the outside world. They bring information in, send actions out, and give life to our engineering ideas.
Now we have met the CPU, memory, peripherals, and pins. But there is an important question.
How do all these building blocks communicate with one another? The answer is simple. Information must move. Inside a microcontroller, information never teleports from one place to another. It travels along special paths called buses. To understand this, let's use a city analogy. Imagine that the CPU is like a company headquarters. Memory and peripherals are buildings located throughout the city. Whenever the CPU wants something, it must send two pieces of information. First, it must tell where to go. Second, it must specify what information is needed. The where is called the address. The address tells the system which location we want to communicate with. Just like every house in a city has its own address, every memory location and peripheral inside a microcontroller has its own address. This information travels on the address bus. The address bus is usually one way.
The CPU decides where information should go and sends the destination to the rest of the system. Next comes the data itself. The data is the actual information being moved. It could be a number, a command, a character, or a sensor reading. This information travels on the data bus. Unlike the address bus, the data bus is typically two-way. Information can move from the CPU to memory, or from memory and peripherals back to the CPU. For example, suppose the CPU wants to read a temperature value from a sensor connected at address 0x100. First, it places the address on the address bus. Then, the sensor sends the temperature value back on the data bus. So the communication sequence is very simple. CPU, then address, then data, then destination. The big idea is this. Inside every microcontroller, information must move to the right place at the right time. Without these communication paths, none of the building blocks could work together. And that is how an entire system becomes one coordinated machine.